Okay, so last week we worked on this 4-bar mechanism. We tried to perform the velocity analysis. And if you still remember, we tried to find the velocity of point C. And right now the input, the angular velocity of the input link is given. So we know the omega 2, the angular velocity of this bar 2. And we try to find the speed of the velocity of point C. So what we've done last week, we found the velocity of B first. But do you know why we don't want to find the velocity C first? We find B instead of C. Why don't we just directly find the velocity of C? If you try to, so right now we use a graphical analysis. We always draw the first line, which is the known one. So for example, this one, we know the omega 2, and we know the length of link 2. So by timing the length of link 2 and times the angular velocity, then we can know the absolute velocity of point A. So we can draw VA first. This one is, we know a direction and we know the magnitude. Then if we want to find the velocity of C, then we probably need to draw another line and try to find, we probably want to draw another 2 lines and to find their intersection, and then we can find point C. And once you find point C, then connect from this origin to C, then you find the velocity of C. But we actually cannot do it right now because if I want to find velocity C, C, then right now in this velocity polygon, I have a point O and point A. So I probably need to find 2 things. One is I find VAC or VCA. Either way is fine. I also need to find VC. I need to find a line representing VAC and another line representing VC. And if I can find the intersection of these 2 lines, then that point is gonna be C. Right now, can we find anything about VAC? Is it possible? So VAC, or I think I use VCA. VCA means the relative velocity between point C and point A. So in this case, because C and A, this one is a rigid link. So there is no deformation between these 2 points. So the length between C and A is always fixed. Yeah. So right now we can find the direction of VCA because it's a rigid link. And right now VCA is considering A as the original point. So for the relative velocity, the only motion C can do is relative to A, is to rotate about this link. So VCA must be in this direction. Because it cannot move in this direction. Yeah, there's no component in this direction. So the only possibility is this one, either this way or the opposite way. I just use one way to represent it. Yeah, it's not going to point him from C to A, so I'll just erase this one. This one is impossible. So that's the only chance. I didn't draw it very accurately, but for your information, these 2 lines, they are perpendicular. So VCA is perpendicular to the line CA. Yeah. So if I try to find the velocity of point C, well, from this position diagram, I know the direction of VCA. So I can already draw a line in this original, in this velocity plot. So I know VCA is just temporary. I know VCA is going to pass the point A in this velocity diagram. But currently, we don't know the magnitude of this one. We only know the direction. So I just draw a line with a random length. But the direction is, this one is the same as this one. This line is representing VCA. So in order to find VC, I also need to find this line. I also need to find VC. But right now, do we know VC? Do we know any information about VC? Do we know the magnitude of VC? Probably not. How about the direction? Yeah, we don't know the direction either. Yeah, because right now this one is not fixed into any link that's connecting to the ground. It's like floating here, and we don't know where it's going. At least by current information, we don't know where this point C is going. So we cannot find another line to represent VC. So that's why we didn't go with finding VC first. Last week we found VB first instead of VC, because we want to see if we find VB, then maybe we have a chance to use this new information VB to find VC. If you directly try to find VC, right now it's impossible because we have no information. We have no direction or the magnitude information about the velocity C. Yeah. So we cannot go with C directly. We can go with B. So last week, just a quick review. We found one line. This one is VB. Because point B is on this link 4, and link 4 is connecting to the ground. So I know the point B. Sorry, cell phone. I know point B is pointing either to this direction or the other direction. It's not going to have any component in this direction, yeah, because the length is fixed. So the only chance is either to the left or to the right. Yeah. So we know the direction of VB, so we can just draw a line with unknown length. Yeah, and it's passing the origin. Yeah, because the VB is the absolute velocity, so you will be passing the origin. VB you can also write as VB/O. That means there's a relative velocity from point B to origin. And another one is we can also find the relative velocity of VBA. That's what we've done last week. So BA, because the length of AB is fixed, so we know there's no component in this direction. There's no component. So the only possibility is VBA is in this direction. So we draw another line in the velocity diagram. So this line and this line, they are in the same direction. And this line is representing VBA. This one is representing VBO or VB. So I know the intersection of these two lines must be the point B. because this line need to pass B. This line also need to pass B. So this point is the only chance where B locates. Yes?
How to find the angle at which we need to draw the
VBO. You mean the angle of VBO? Yes. VBO, this line, the direction is the same as this one. And this one is perpendicular to the bar 4. Yeah, because the bar is fixed. So when it's rotating, yeah, the velocity must be perpendicular to the bar, to the link. Yeah, so by doing so, we can find the magnitude of VB and VBA because we already find the point B in this velocity diagram. So once we find this point B, well, we already find the velocity of point B. So if you want to find, because originally the angular velocity is given, so we know omega 2. We probably also want to find omega 4. Maybe. Well, in this question, we want to find VC, but let's say if we also want to find omega 4. Can we find omega 4 by current result? Right now, we already know VB. What's the relationship between VB and omega 4? VB is basically omega 4 times the length O4B. Right? So if I measure the length of O4B and I divide VB by O4B, I can get omega 4. And how about omega 3? Omega 3 is the angular velocity of this link, of this triangle. So we can do the same thing. If we already know VBA, if I already know VBA, then I know VBA is gonna be omega 3 times the line AB, the length of the line AB. So I just measure the length of AB, and I divide this VBA by length AB. I can get omega 3. So by drawing this triangle, we can already find, well, VB, VBA, and also omega 4 and omega 3. Any questions so far? So here we can get, well, they are overlapping. So here I can already find omega 3, yeah, by using this relationship between the linear velocity and angular velocity. So if we get the omega 3, maybe we have, here I said we can obtain VCA, but we don't know yet. I think we can use this information, this omega 3, to find VCA. How can we use omega 3 to find VCA? VCA is C relative to this point. So VCA is actually CA times omega 3. Yeah. So CA, you can just measure CA from this diagram. So once you get the CA, the length of CA, you can just substitute the CA with the value, and we know CA and we know omega 3, so we can get VCA. Any question for this one? So the direction of CA is perpendicular to the line CA. Yeah. So VCA for this question is this one. I change the color. Oops. VCA. VCA is in this direction along the blue line. It's perpendicular to the line CA. Okay, so once we get the VCA, then our purpose is to find VC. So what is VCA? If we know the VCA, if we know VCA, VCA can be written as we can simply use the relationship to find VC. Because now we already know the velocity of A, and by using this equation, we can get VCA, and we know the direction of VCA. So you just sum these two terms up. Then here I still use the velocity particle. We know the direction of VA, direction and magnitude of VA, and we know the magnitude and direction of VCA. So basically, this point is gonna be C in the velocity diagram. So you simply connect this point to this point, and this is gonna be VC. You can just directly measure it and to get the magnitude of VC, and also the direction of VC. Any questions? So here, just a quick review. Because initially, we tried to find VC directly, but we found it's impossible. So instead, we find a VB first, because B is on the link connecting to the ground. So it's possible to get the direction of VB. So that's why we obtain VB first instead of VC. And once we get the information, we draw this velocity polygon, then we know we can obtain the omega-3, omega-4 by this diagram. And once we get the omega-3, we can just substitute and to get the VCA. You simply add VA and VCA, we can get VC. Any question for this one? So, and actually there's another method. So I call this method 1. Method 1, we find VB first, and then we use this new information, omega-3 and omega-4, to find VC. But there's another method. Well, it's very similar, but slightly different. In this plot, we draw VB and VC in two different plots. In this one, I'm going to draw everything in a single plot. But well, it's very similar to the previous one. We still find VB first instead of VC. Well, so the procedure is the same as the previous one. Well, in order to find VB, we need to find, in order to find the point B in the velocity particle, we need to find VB and we find a line. Well, this is the same as the previous method. So we find point B in the velocity particle first. And then we can obtain the VB and VBA. But this time, I'm not going to calculate the omega 3 and omega 4. I'll just directly use the current result. Right now I find point B and I know A and O. I just use these 3 points and try to find where C locates. So right now we get this VB, VBA, VB and VA. What we can do next is we can try to find 2 lines. So we always draw two lines with unknown length, but with known direction. And we find the intersection of the 2 lines, then the intersection is gonna be the point we are looking for. So right now we try to find point C in this velocity particle. So in order to find point C, we need 2 lines with known direction. And right now we have point A, B, O. So what I can try to do is, if I can find VCA and VCB, and I find the intersection of these 2 lines. These 2 lines, the magnitude is probably unknown for now. But we may have a chance to know their direction. Yeah. VCN and VCB. Okay. So let's do VCA first. It's already shown here. Yeah. What would be the direction of VCA? The direction of VCA is going to be perpendicular to the line CA. So we already know the direction of VCA is this direction, this green line. Yeah. We don't know magnitude yet, but we know the direction. And we know this VCA is going to pass VCA is going to pass point A in this velocity diagram. Yeah. So this VCA, we know it's going to pass point A in this. It's going to pass both C and A in this velocity diagram. But right now we only have A, so we just draw a line and then a line pass point A. So this line is representing VCA. We don't know the magnitude yet. And if we can also find another line to represent VCB, then the intersection is gonna be point C. So let's see if we can find VCB. So VCB, we know the length of VCB, line CB is fixed. So VCB is C relative to point B. So the direction of VCB, it must be perpendicular to the line CB or BC. So here I draw another green line here. This line is perpendicular to the line CB. And I know this line in this velocity polygon is going to pass the point B. It's going to pass both B and C, but right now we only have B. So we just let it pass point B. So this line is representing VCA, it's VCB. So both this VCA and VCB, they need to pass point C. So the only chance is this intersection is going to be point C. So yeah, you can draw from point A to point C, and that line is representing VCA, and this line is representing VCB. If we want to find VC, just connecting from this origin to point C, and this line is going to be VC. So this is another method, different from the previous one. Not so much difference. The only difference is we didn't calculate any omega. We just directly use this new. Original we have O and A, and we find point B. We use this point B and to draw some new lines. And yeah, just by manipulating these lines, we can find the point C without doing the angular velocity calculation. Any question about this one? Yes? The magnitude of VC? Yeah, we just measure the length representing the magnitude. Yeah. So this one is a vector. The vector includes the information of direction and also magnitude. So the length of this arrow is the magnitude of the velocity. Yeah. Right now I didn't put any numbers, so yeah, later I will just draw an example with the scale so we can know how the number goes. But this one, yeah, because I didn't say omega 2 equals something. So I just randomly draw the length of VA. Any other questions? And just one thing to point out. In this diagram, we also, in this original position diagram, we have a triangle ABC. Here we also have a triangle ABC. I didn't label this point with C, but this point is C. So do you think these two, what's the relationship between these two triangles? Pardon me? The scale? Yeah, the scale. So you think they are the same, but just with different scale. Do you think they have any relationship, or they just two different triangles? Scale and angle. Yeah. Right. Yeah. This triangle is, these two are similar triangles. That means they're the angle within these three angles are the. So this, if I call this angle A, this angle A is the same as this angle. And this angle C is the same as this angle. Angle B the same as this angle. So we call them similar triangles. Yeah, and their orientation are different. Well, obviously they are different. Yeah. This one is, the angle of this one or the orientation of this one is this one you rotate by 90 degrees. Yeah. Remember how we get this let's say VBA or VCB or BCA. This VBA is perpendicular to this this BA line. So this line and this line, they are the angle between this VBA and this and this line BA are 90 degrees. And also this CA, this line CA, and this VCA, they are perpendicular. So all these three sides of this triangle are perpendicular to the side of this triangle. So they are similar. These two triangles, they are similar. And the only difference, the scale is different, and also the orientation is different. This one is, you rotate this one by 90 degrees, and you can get this one. So you may figure out there's a faster way to find this VC. Because we already know this one and this triangle, they are similar. So if I back to this step, once I find this VBA, I can just draw a similar triangle, similar to this one, and the endpoint of this triangle is gonna be point C. You don't even need to draw the other two lines. Yeah, just another trick to do this analysis. Any questions? So here I'm going to do another example. So I'm going to use a crank slider, and also to perform the velocity analysis. So suppose we have a, sorry, I need to switch the monitor. Okay, so we're going to analyze to perform the velocity analysis of this one. And the angular velocity of this bar is given, and we try to find, let's say we try to find VB. I try to find VB. So yeah, and this time the value of the omega-2 are given, and we'll just directly measure the length of this link, so we can get the velocity. So right now the omega-2 is given as 10 radian per second, and I already measured the length of OA is 40 millimeter. Yeah. Can use this ruler to measure it. So I'm represent, yeah. So for graphical analysis, you are going to do it in this way. So use a ruler to measure the length of the bar. Yeah. This one is just one-to-one scale. So I measure is 40 millimeters. So I just write it down. OA is 40 millimeter. Yeah. I think that's all we know for now. So I know the length of OA is 40 millimeter, and the omega-2 is 10 radian per second. Then we can already calculate the VA. So I write it here, VA. So what would be the value of VA? So VA will be simply you times OA times omega-2. So it's 40 millimeter times 10 radian per second. So it's 400 millimeter per second. So that's the velocity of A. Any question about this one? And what's the direction of A? The direction of A is going to be perpendicular to this OA line, right? And we know a direction is pointing to this direction. I'm not going to draw it because it's hard to erase it here. So yeah, you know the direction is pointing from this point to that direction. Yeah. So yeah, I need to draw this VA in the velocity polygon. And right now this one is 55 degrees, so I need to rotate it by 90 degrees. So 35, 35, 90, yeah. So I'm going to draw this one here, this VA. Sorry, I should draw it in scale. Right now it's 400 millimeter per second. And here I use a scale. I use 10 millimeter to represent 100 millimeter per second. It's just a scale I set for this case. But it depends on how large your paper is. Maybe you can use a larger scale or smaller scale. That depends on your space to draw your diagram. So here, 100 millimeter per second is represented by 10 millimeter. So right now VA is 400 millimeter per second. That means I need to draw 40 millimeter to represent VA. So 40, 4 zeros, 1, 2, 3, 4. So 40 millimeter here. And this one is gonna be VA. Any questions? And we try to find VB. We try to find the velocity of B. And so very similar to the previous 4-bar linkage case, I'm gonna use another color. So in order to find, right now we try to find VB. So we know VB can be represented as VA plus VBA. So what I'm trying to do is, well, I already have VA. So if I can find a VBA and VB, then I can find the point B. Do we know any information about VB? Either direction or magnitude? We know the B is on this slider, so it must be moving along this horizontal line. So we know the direction of VB must be in the horizontal direction. We don't know if it's pointing to the left or to the right, but I know it's on this horizontal line. Yeah, but we don't know the magnitude yet. But I should label this O and A. Right now we only know the direction of VB, so I just simply draw a line, horizontal line, because I know VB must be lie on this line. So this one is representing VB. And we also need to find VBA. Do we know any information about VBA? We don't know the magnitude yet, but still we can also find the direction or the orientation of VBA. VBA must be perpendicular to this line AB. So must be perpendicular to this one. Yeah. So I'll rotate it by 90 degrees. Yeah. So yeah, there will be a direction. It's perpendicular to line AB. And I know the VBA is going to pass the point A. It's going to pass both A and B, but right now we only have A, so we just go with A. So you just align the ruler with point A and draw another line. So this line is representing VBA. So we got a line representing VB, another line representing VBA. Oh, sorry. So the intersection of these two orange lines must be point B. So once we get the point B, I know the VB is gonna be, VB is pointing from origin to point B. So it must be this one. So This is VB. This is VBA, pointing from point A to point B. So how can we, so we've done the analysis. So now if we want to get the value of VB, we simply use this ruler to measure it. So let me measure it. So how large is it? So 1, 2, 3, 4, around 45 millimeter. So VB, I measure it, is 45 millimeter. And in the scale, we say 10 millimeter is representing 100 millimeter per second. So it's 450 millimeter per second. So that's the absolute velocity of point B. We can also measure VBA. So it's 2.27. So VBA is 27 millimeter. So it's 270 millimeter per second. Yeah. So if we also want to find the angular velocity, let's say I want to find the angular velocity of, we already know omega 2. And so let's say I want to find the angular velocity of R3, so omega 3. So omega 3, we know VBA is gonna be omega 3 times AB. So right now we already know VBA. If I can measure the length of AB, then I can use the equation to find omega 3. So let's measure how long AB is. So 1, 2, 3. Let's see. 1, 2, 3, 4, 5, 6. 6 point something. 64. So I'll just write down here. AB is 64 millimeter. So I know this 270 millimeter is going to be 64 times omega 3. So you can calculate omega 3 by using this relationship. So omega 3 is 270 divided by 64. 1, 2, 3, 4, 5, 6. Yes. So that's how we use graphical analysis to help us to find the velocity of a linkage, of any point in the linkage, or the angular velocity of certain link. Any question for this one? Okay, so just an announcement. So we'll have our very first quiz on October 15th. So still have 2 weeks. So quiz 1. It's Monday. So quiz 1. So October 15th, I think it's Monday. And yeah, the same, our lecture time. And the range will cover from mobility to position, velocity, and acceleration, which we haven't covered yet, analysis. But I think I'll way more on mobility and velocity analysis. And I'll post some assignment for you to practice. I think I'll upload it today, and you can just practice by yourself. I also upload the solution. So if you don't know how to do it, yeah, you can just refer to the solution. Okay, any questions so far? And then we'll move to the, just one thing to remind you. So in this case, in the 4-bar linkage, when I say 4-bar linkage, I mean this one. I mean this 4R linkage. It's a linkage with 4R joint. For this one, if I say this O, A, B, C. In this case, all the lengths of links are fixed. So if I say OC, CB, AB, or OA, all the lengths are fixed. But in this one, you can see the situation is a bit different. OA is fixed, AB is fixed, but OB is not fixed. Yeah. We probably don't feel anything bad for now, but when we do the acceleration analysis, you will see the difference between this one OB. The length of OB is gonna change when this mechanism is running. So when we differentiate it, yeah, you do the time derivative of OB, then the value is gonna change. Yeah. And these two cases, in this case, only the length change. And in this case, only the orientation change, only the angle change. But in a more complicated case, it may happen that both the orientation and the length change. In that case, yeah, the acceleration analysis is going to be very complex. So we'll see that in the second part of the graphical analysis. So we're going to move to the acceleration analysis. And it's a bit more complicated than velocity analysis. But just a quick review. So what exactly is acceleration? So acceleration, by definition, is the rate of change of velocity with respect to time. And for the link, we have two types of acceleration. One is the angular acceleration. So it's a time derivative of omega. Omega is the angular velocity. Also, we have a linear velocity, linear acceleration. Sorry for the mistake. So linear acceleration is time derivative of linear velocity. So suppose we have a link. Actually, two links connect together, and we are trying to define the velocity of point B. Yeah. Just take a look of PA first. So A is on a slider, so it can move in this horizontal direction. And PA is a bar connecting to the slider, but the length of PA is not going to change. So the length of BA is fixed. So we try to define the acceleration A, P/A. There's the acceleration of P with respect to A. So it's still the relative acceleration of P to A. Yeah. So for acceleration, yeah, we can represent the acceleration in this way is time derivative of BPA. So in this case, if we want to find if we want to find AP, we'll use similar relationship. If I want to find AP, I can use A plus APA. So we want to find AP, and we need to figure out what's AA and what's APA first. And A, suppose we already know AA is in the slider is with certain acceleration. Suppose we already know it. So just draw it here. And suppose we also know the acceleration of APA. We know a relative acceleration. Then we just draw the relative acceleration starting from this A point. One thing I want to mention here is when we consider the acceleration, in this case, there are two components of acceleration. One, I call it tangent acceleration, and we write with a small t on the top. So for PA, for this think PA, APA is a tangent, so it's in the tangent direction. When I say tangent, it's perpendicular to this bar. So this acceleration APA may have a tangent acceleration. It may also have a normal direction, acceleration component in the normal direction, and I label with an N. This is probably the centripetal acceleration. So for acceleration, it may have tangent component, may also have a centripetal or normal component. So actually this one is just not a single acceleration, it has two components. And we need to combine these two components together to get the resultant acceleration APA. So in this part, this acceleration diagram or acceleration polygon, or very similar to the velocity polygon, we also label this OA or the point B. But here we want to make it different from the velocity polygon, so we make a small plum. So when you see the plum, it indicates this plot is an acceleration polygon or acceleration plot. But otherwise, there's no much difference. Yeah. So we still draw the vector, but right now it's the acceleration vector. So for the normal or the centripetal acceleration, well, it's always pointing from B to A, yeah, from the point to the origin. So yeah, it has a normal component in this direction. We know the direction. Also, it may have a tangent component. So tangent component is perpendicular to this one. Yeah. So we need to combine these two together to get this resultant acceleration. Here I just randomly draw the magnitude, but this depends on how large your tangent or normal component are. The length might be different. So if we take a look of how the normal component and how the tangent component, they take a look of their representation or their equations. The normal component is basically, or is, I say centripetal component, so it's basically omega squared times the length or the radius. This one is rotating about this point, so the length is length PA. So I just represent as RPA. Yeah, and omega 2, this bar is omega 2, so that's the angular velocity of this bar. So normal component can be represented in this form. How about tangent component? Tangent component is gonna be alpha. Alpha is the angular acceleration. So angular acceleration times the length of the bar. It's gonna be the magnitude of a tangent component. Yeah. So yeah, in this part, yeah, you may draw the tangent component, normal component, and I know the resultant component is gonna be, yeah, you draw a rectangle, then there's a diagonal line. It's gonna be the resultant acceleration. Any questions? So here I just want to say, yeah, for this acceleration, we may have more than one component. In velocity analysis, we haven't encountered this type of situation. We always only have one component. But right now, even this APA, actually we can divide it into two components. Yeah. And these two components, they are actually independent. So, okay, move to the next page. Oh, back to this one. So by this representation, we can actually find, yeah, even this one is the acceleration term. This one is a centripetal acceleration. But when you see a representation, it's formed by omega. Omega, we can obtain omega in velocity analysis. So actually, if you've done the velocity analysis, we can already get the this normal component or the centripetal component, yeah, just by doing the velocity analysis. We don't need to perform acceleration analysis in order to obtain this term. Yeah. Once you've done the velocity analysis, you can get this one immediately. But for this tangent one, if this alpha 2 is an unknown, suppose it's not input, then alpha 2 is something we need to find in the acceleration analysis. Yeah. So omega 2 will be obtained by performing the velocity analysis. But to get this alpha, this angular acceleration, we need to perform acceleration analysis to get this one. Okay, any questions so far? So then we'll move to this example. So we'll still use a polygon. Here we just call it vector polygon. It's not necessary to be velocity or acceleration. Yeah. So before we perform the acceleration analysis, we need to perform the position and velocity analysis first. And then we can move to because yeah, we need to know the position of the mechanism. We also need to know the velocity information in order to perform acceleration analysis. Yeah. So here I just assume we've done that. So we know all the position information. We know the angle of the four links, and the length is for sure known. And also, I already assume we've done the velocity analysis. So we know all the omega of all these four bars. And right now we are providing an input on link 2, so on this link. And the alpha 2 of this link, the angular acceleration of this bar is given. So this one is known. Yeah. And we try to find the acceleration of point B here, and also try to find the acceleration ABA. So it's B relative to A, and the tangent component. Yeah. So tangent components are related to alpha, related to the angular acceleration. So we must perform acceleration analysis in order to acquire these two. So it's very similar to the velocity analysis. We just draw what we know, or what we know first. So here, because alpha 2 is given, so I can get this AA tangent. I can get a tangent component of this acceleration. So I'll just write on the board. So because angular acceleration of input is given, so I actually can directly get this AAT just by using this expression. So we simply measure the length of O2A, and then times the angular acceleration, then I can get the tangent component of point A. Tangent component of the acceleration. And for the normal component, well, it's basically the centrifugal acceleration. So it's omega 2 squared times the length of O2A. So we can also obtain it right after we finish the velocity analysis. So in this diagram, I can just draw this AA is relative to the origin. So I just connect these two together. This one is a tangent component, and this one normal component. So the summation of these two is gonna be the total acceleration of point A. Any question for this one? You can either draw this one first or this one first. It doesn't matter because they will eventually have the same result. So here we can obtain this AA by those nodes. And our goal is to find the acceleration of point B, the tangent component. So we'll still draw some line and to find their intersection, just like what we've done in the velocity analysis. But first we need to know what information do we have so far. So to find the tangent component of AB, well, we can see what we know about B. If you still remember, the normal component or the centripetal component of point B, we can also represent it as something we already know. So it's O4B times omega 4 squared. Yeah. O4B is the length of link 4. B is on this point. Omega 4 is the angular velocity of this bar. And because we already assume we've done the velocity analysis, so all the velocity are known. So this term should also be known. And tangent component. This is what we are going to find in this analysis. So it's not unknown. currently we don't know alpha 4, so we'll just leave it here. So remember how we do the velocity analysis? We just try to draw everything we know on this plot. And currently we know this one, we know it's ABN, so we just draw it. Oh, we also know another thing. I draw another part first. So we may also want to know A, B, A, N. A, B, A, A, B, A. Well, they all have very similar expression. So we also know the normal component of ABA, or is simply the length of line AB times the omega 3. Omega 3 is where AB locates. Omega 3 squared. So you can get this one just right after we've done the velocity analysis. Yeah, and ABA, because it's centripetal acceleration, so we know it's pointing from point B to point A. So you see it's the arrow here. It's pointing from B to A. Yeah, and it's along the line AB. So this one, this green one is the same with this one. The same direction, but I change the magnitude a little bit to make it more clear. But this one is actually the same as this one. So here we also get this ABAN. And as I mentioned previously, we can also get it ABN. And the direction is pointing from B to 04. So it's this direction. And because it's passing O, so starting from point O. And yeah. For these two normal components, we know both the direction and magnitude. So I just draw a solid arrow. Okay, so next step. So we already finished this one, this one, this one, this one. So we still have two unknown. We still have AB and ABA. Just for your information, we still try to draw a triangle representing this relationship. Now, so in this diagram, I'm going to draw everything about these three. They are going to form a closed loop. Okay, so we still have two unknown, this ABT and this AB/AT. Yeah. But we may have some information. We may not have full information about these two, but we may have some information that allow us to draw something on this diagram. So what do we know about this one? It's ABT. We don't know a magnitude yet, but we know the direction must be perpendicular to this B04. This ABT must be on this, indicated here as PP line. Yeah. ABT must be in this direction. Yeah. And ABAT must be perpendicular to this line AB because it's tangent, so it's perpendicular to AB. So we know a direction, but we don't know a magnitude yet, but that's fine. We just draw the direction. And we know ABT is going to continue from this one. So you will continue to draw this ABT here, and you will continue to draw the ABAT right after this one. So here I just draw the ABAT. Yeah, the direction is perpendicular to this line AB. This one, the same as this one. And also I can draw this ABT. Just continue from this ABN. Yeah, just pass in the endpoint of ABN and yeah, just draw it with the same direction as this one. So we know this two line is going to pass point B. So the only chance is this point is point B. So that means we already find the point B in the acceleration polygon. So back to this question, we need to find ABT and ABAT. Now you simply just connect them from this point to this B, from this point to this B prime. Then we can get this ABAT and ABT. Yeah. So more component for the acceleration analysis, but the basic concept is pretty much the same as the velocity analysis. Yeah. Any question for this one? So if we want to find, currently we find the ABT. So if we want to find omega 4, you can use this relationship. So you measure the magnitude of ABT and just also measure the length of O4B. And you just divide this one by this one, you can get alpha. Any questions? No? So we already found B. We found the acceleration of point B. So let's just continue to work on this one. Let's say we also want to find acceleration of point C. So, okay, sorry. Okay, so from the previous step, we already found this ABT and this ABAT. So here I just assume we've done the previous step, so we know the omega 3 and omega 4. So suppose all these are known. And we want to use this information, we want to carry this information and to help us to solve the AC, acceleration of point C. So let's just work on it. So here, I'm going to use another, you know, AC can be represented as AA plus ACA. So we'll try to draw a polygon include all these three terms. Yeah, and we already know all the information about point A. So this is the same as the previous slides. So I just draw the same thing as the previous slides. So we already know AA, but we try to find ACA. And if I can find ACA, I just combine these two together, I can find AC. So for ACA, the same as this one. here we already know this one is because ACAN can be expressed as omega 3 squared times CA. And omega 3 is already known, so we can draw this one directly. And the direction is pointing from C to A. So this direction is the same as the direction of line CA. Yeah. And also the tangent component of ACA, because from the previous step, once after we find a point B, we can obtain this one, then we can find alpha 3. So we just apply the previous, the result from the previous slides, alpha 3, into this expression, then we can find ACA tangent component. So I can just draw it here. And the direction is perpendicular to this one. So right now we try to find ACN or ACT. And we actually have no information about these two. Yeah, because the absolute velocity of this point C it's like floating here. We don't know the direction of this one or this one. Don't know yet. So how can we find it? Well, indeed, we don't need to find these two, because by doing so, we already find point C. So you just connect this point to this point. Then we get the absolute value of point C. Absolute acceleration of point C. Here it's not asking normal component or tangent component. Or for this one, actually there's no tangent or normal component. We don't know how to define a normal or tangent for this point. So we should just get this, this AC. Yeah, because the floating here, so we cannot define what's normal, what's tangent for this point. It's not relative to a certain point. So for this point C, we use the info. We obtain this velocity acceleration of point B first in the previous slides. Then we carry this information into this diagram and to find point C. And once we find point C, we can connect the origin to the point C and to get the acceleration of the point C. Any question about this one? No? So just work on more examples. So here is a different mechanism. This one is called Scotch yoke mechanism. So it's working a bit like a crank slider. We use this link 2 as the input, and link 4 is the output. So link 4 is a slider, and link 3 is also a slider. So once you rotate this input, this link 4 is going to move to the right or to the left. It's going to move horizontally and back and forth. Yeah. So it's very similar to a crank slider. Yeah. So, okay, so for this one, we're going to do the, here in this slide, I'll do the acceleration analysis, but let's do the velocity analysis first. Let me switch monitor. Okay, suppose we don't know the velocity yet. So we do the velocity analysis first. Let me open the new slides. Okay. Let me just. So let's try to find a velocity first. Velocity B. So the velocity are unknown for now. So we try to find VB. B is a point on link 4. So B is moving with link 4. Here, this question is overlapping point A and point B. It's saying A is on 2. So A is on this point. But B is also on this point right now. And he said B is on 4. But once you move this one, and just draw another one. So next step, we will move here. Keep moving. So it's like this. It's moving, and the slider. Once you rotate, you will become like this. The new position will maybe in this orange position. What is saying B on 4? That means B is following link 4. So in the orange plot, B will be on this point. So it's the same location. Should be a bit lower. So B is on the same location relative to link 4. But A, so in this case, this A, and this B. At the first step, they are overlapping. But just for your information, you will see this type of description often in the future. You may say that A on something and B on something. And in the initial position, they are overlapping, but actually they are representing 2 different points. So once they move, the A will follow this link 2, but B will stay with link 4. So B will still at this position, but A will move to this position because it's following link 2. So that's what A on 2 and B on 4 means. Okay, so we try to perform the velocity analysis and try to find VB first. And currently, because we already know omega 2, so we can directly get the velocity of point A. So what's the velocity of point A? Velocity of point A is perpendicular. The direction is perpendicular to this line, to this O2A line. We'll do it with its initial position. So in order to find VB, we'll probably use the same relationship. VB equals VA plus VBA. Yeah. And we already know VA because VA is omega 2 times O2A. So it's in this direction. Suppose it's rotating counterclockwise. So this VA is in this direction. I just randomly draw the magnitude. Yeah. Yeah. Because I didn't provide a number here, so I just randomly draw one. Yeah. And we also need to find, so I just label this point A and point O and point A. Now I also need to find VBA and VB in order to complete this polygon. Do we know any information about point B? You see, a point B is on link 4. And link 4 is a slider, so it's only move to the right or to the left. It can only move horizontally. So that means point B is on link 4. So that means point B will also move just horizontally. It can only move in this direction. Yeah. But we don't know the magnitude yet. So I know B must be moving in this direction, horizontally. So I can draw the direction. So it's VB. I use another color. Okay. So that's VB. We only know the direction, but we don't know magnitude yet. And how about VBA? Do we know any information about VBA? You can see here. VBA. What would be the direction of VBA? For sure we don't know magnitude, but we probably will be able to draw a line somewhere here and find the intersection of VBA and VB. Then we can define the point B in this velocity plot. But just like the previous examples, we always know a direction, but without knowing the magnitude. But right now, do we know the direction of VBA? What would be the direction of VBA? If you see these two, this orange plot, B and A, if I'm standing on A, I'm standing on point A and I'm seeing point B, I will only see point B going far away from me or closer to me. It's always along this direction, right? Suppose you are standing on point B. You will see B going further or coming closer, but it's not going to left or going to right. See, because A is a slider, A is on a slider. Right now we only concern point A and point B, so I just draw them here. If I'm standing on B and I'm looking at point B, when it's moving, or maybe next moment, it moved to this point. So maybe next moment it moved to this point, but no matter how it moves, the only relative displacement or velocity is always in this direction. It can be further, it can be closer, but it's always in this direction. So the relative position or relative velocity or even acceleration for point A and B is always in the vertical direction. So here, although we don't know the magnitude yet, but we can know the relative velocity between point A and B is VBA. It must be in the vertical direction. And it's passing point A and point B. Right now we only have A. So you just draw a line crossing point A. So this one is V, B, A. Yeah. We already get VB and VBA. So we know the intersection of these two green lines must be point B. So once we get a point B, or you just connect from the origin to point B, then you get the velocity, VB. And if you're also interested in VBA, or just connecting from point A to point B, then that's VBA. Any questions? No question? So once we finish the velocity analysis, we can obtain those values, those velocity informations. Then we can move to the acceleration analysis. So for acceleration analysis, well, it's similar to the previous acceleration example. Okay. So we'll use similar relationship. This one is A and B. So we'll still use this AB equals AA plus ABA. And we try to find if we know any information about them. Right now, because the input acceleration is given, so we know AA. We know everything about AA. We know the AA normal and AA tangent times volt. This one is given in this, the input is known. So this one is given, so you can just substitute the value inside and to get the magnitude. Also, the normal component is known. It's omega 2 squared times the length of the bar. So these two are known. You can just quickly draw them. And just to remind you, the direction is along the direction of this line. And this tangent component is perpendicular to this one. So we know these two, so we can find the resultant acceleration of point A. But we also need to find the other two. We also find some information about AB and ABA. So you can, so ABA, or you can still separate the component. It's omega ABA. ABA, if we look at ABA, ABA is the line I mentioned in this diagram. Because BA, although the length may change, but they never rotate. So they are not going to have any angular velocity or acceleration. The only possible this one may have acceleration is in this direction because they never rotate. So there's no centripetal or the tangent component of the acceleration. They may have an acceleration in this direction. So we know the only possibility for this ABA to have acceleration is in the vertical direction. So this one has no tangent or normal. We don't represent as tangent or normal component. We will give it a name later, but let's just call it ABA for now. Yeah, because we know the only chance this one to have acceleration is in this direction. So we know ABA, and we also try to find AB, the acceleration of this one. And as we mentioned previously, because B is on this link 4, and link 4 is only sliding in the horizontal line. So the only chance for AB to have something is it must be in the horizontal direction. It may be 0, but if we have something, it must be in the horizontal direction. And this AB must be passing the origin, passing point O. This ABA must be passing the point A. So we obtain a line for ABA, obtain a line for AB. So the intersection is going to be the point B in this acceleration diagram. So simply connect this O to this B. You can get the acceleration of point B. Okay, any questions? No? So that's it. So I'll see you next Monday.